Hi Year 12, let's have a look at your graph skills in lesson 6 then. So task 1 was pretty straightforward. You just needed to look at the graph, look at the error bars and state what the uncertainty was for both time and distance. So what you need to do is, sorry you can hear my rowdy dog in the background. So he's very distracting. The error bars here, you're going from the actual point to the extremity, so the error bar value is plus or minus this distance here, which is 0.5. So you can see from the right hand side of the point you've got plus 0.5, from the point to the left you've got minus 0.5, so time should have just been 0.5 as your absolute uncertainty. And then distance was a bit harder to see, but the distance was 0.1. It was plus or minus 1 small square. So that one should have been pretty straightforward. On your second one, you were asked to plot error bars for both mass and extension. Now use pencil, please, but I've done it in pen just so that you can see it a little clearer on the video. So we know that the uncertainty in the mass is plus or minus half a kilogram. Half a kilogram is 1 small square, so you need to be plus a small square and minus a small square on both sides for each. And then the uncertainty in the extension was plus or minus 10 millimeters, which again is 1 square, but the points don't lie necessarily on one of the grid lines. So I had a little look and I measured the scale, and for me 1 square was 4 millimeters. So therefore I needed to be plus or minus 4 millimeters either side for my error bars in the y-axis. So I literally just got a ruler, placed the ruler down at 0.4 and then marked either side and went from there. So you do want to be very careful and make sure that that is accurate. So in question 2 you were plotting this data on a table with error bars given as sorry, that should be a plus or a minus here. That's not great, is it? That should be a minus sign there. Plus or minus 0.1 volts. And same, but for current it's plus or minus 0.01 milliamps. But you weren't asked to put error bars on there. And actually, in reality, you're very unlikely to have to plot error bars on both axes. It will only be one in most circumstances. So you were plotting the points, then adding a line of best fit, calculating the gradient, and then adding lines to show the greatest possible worst gradient and the least worst gradient. So shallowest and steepest, calculating the values, and then finding the biggest difference between the two. So I plotted it, but it's been scanned, so it's not the best quality graph. But you should see, just a little bit more, here we go, that's a bit better. So you should see a couple of things. Going up in 0.1s for my milliamps so that I get a good spread. Going up in 0.5s for my volts. You can see where I've marked the points. If I then zoom in a bit closer, you will be able to see the error bars. This is why it's important that you cap the error bars and put little dashes either side so that they're a bit easier to see. I've done my best fit with pencil. I've then used colour to indicate my steepest and shallowest worst lines. So because my error bars are on my x-axis, to get my shallowest, I'm going to go from the very far left of my bottom error bar up to the very far right of my top error bar and then line through there, and all points have their error bars still lying on that line, so still valid. And then for steepest I'm going for the extremity on the other side, so the far right of the bottom error bar to the far left of the top, and again straight line through, all error bars still lie on that line. So all three of these are valid. because they all pass through all error bars. So to calculate your gradient, you're then going to add a triangle. I've chosen some points. So these are 2 coordinates of my line of best fit on my grey line. Gradient is just change in y over change in x, so I get a value for my best fit line. You should be able to get a gradient of your graph. You do exactly the same for your worst fit line, you just choose 2 new points. I can see, if I zoom in and let it settle, hopefully you can see that there is more of an extreme between the grey and the green than there is to the pink. So there's a bigger uncertainty if I go for my green. So that's the one that I am looking at. I took 2 new points, found the gradient of my green line just by finding the gradient, as you always would, and I get a new value of 6.95. I find the difference between the 2, and that is my uncertainty. So this is my uncertainty in my gradient. So you should have got something along the lines of 6.6 plus or minus around 0.3. Obviously yours is going to be slightly different because you've plotted it slightly different, and there's always tolerance in the exam, so don't panic. But you want to not be too far out. If you've got something crazy different, send me a little message and we'll go through it together in a bit more detail. So then we get to the IB question. So this is a paper 3 question. Sorry, for some reason the gamma sign converted to a G, which is very confusing. So the correct equation is here. So we've got a spherical soap bubble made of thin film of soapy water, and we've got an internal pressure Pi, and P0 is the constant pressure of air. And they've given you a suggested equation. So the difference in the pressure is given by 4 gamma over r, where gamma is just a constant and r is the radius of the bubble. So data was collected for these variables, and a graph was plotted. So the first thing I would do is take a look at what has been plotted. On my y-axis, I've got Pi minus P0, and on my x-axis I've got 1 over r. Now this should be kind of ringing alarm bells because the equation that we have includes both of those things. So what I've done is I've separated this out and said I can rewrite the equation as Pi minus P0 is equal to 1 over r multiplied by 4 gamma. Now I know that this is what's on my y, I know that this is what's on my x, so I know that the scale factor that I'm multiplying x by must be the gradient m, because I've got a straight line graph, and I know y equals mx plus c from GCSE is a straight line graph. Okay, so that should already be getting your brain thinking, hang on, there's a link here. So I then also looked at what each square was worth on the grid, because it could be a little bit of a tricky scale here. You can see there's 10 squares between 10 and 12.5, which means that each square is worth 0.25. So just do the little things, don't be lazy, and it should help you count a lot better. So the first thing I did, just because I was looking at some data analysis, is I calculated the gradient. You can see the 2 points that I've chosen. I've read off on my scales. By drawing dotted lines straight down, I'm less likely to mess up and make just an error with my eye, is the easiest way I can explain that. If you just try and read by like scrolling down, oof, that's a sign of the times. Just by looking down, you could very easily lose track and move across. So I would always draw it on. Anyway, we find our gradient using our change in y over our change in x. And I got a gradient of about 0.1. I then chose a point in order to find my y-intercept. So I chose this point here, I think, if I can remember correctly. So it's very important that you don't just draw a line back and go, oh, here's my y-intercept. Look, this is not the origin. Okay, it's a false origin. So when this crosses the y-axis line, that's not actually at the intercept. So that's why I need to plug numbers back in. So I chose 12.5 for x, and that worked out to be 1.1, 1.2, 1.25 on my y as well. So I then popped my y minus mx values in. So my y value that I chose was 1.25. My gradient I'd already calculated. My x value was 12.5. And that told me and proved to me that actually the y-intercept will be 0. Now this is going to be helpful for some of the questions, so I might have to just revert backwards and forwards between these pages. It says, suggest whether the data are consistent with the prediction. The prediction is the equation, right? So the equation should be holding true if I can see that pi minus p naught is proportional to 1 over r. Okay, this is my equation. If I can see that pi minus p naught is 1 over r multiplied by 4 gamma, this is just a constant of proportionality, and therefore this and this must be proportional. If I see proportionality on a graph, what I'm expecting to see is a straight line graph through the origin. Okay, well, my prediction is correct. I do have a straight line graph through the origin, and I've proved it with my data. And so therefore, if this is what the data showed me, it does align with this style of equation. So I've proven that my theory is looking pretty good. So therefore, the data is consistent with the theory. If that's still not making sense to you, ask for a phone call with me, because you do need to make sure that you're happy with proportionality. The next part of the question asks you to prove that the value of gamma is about 0.03. So again, we know we have a straight line graph, which is y equals mx plus c, but plus c was 0 because it went through the origin. We know that we plotted pi minus p naught for y. We plotted 1 over r for x, and so therefore the gradient of my graph must be equal to 4 gamma. I calculated the gradient to be 0.1, and that is equal to 4 gamma. So I can rearrange that and say that if 4 gamma equals 0.1, then gamma is equal to 0.1 over 4. When I do that, I get 0.025 on my calculator. Okay, that is, to two significant figures, 0.03. And it only asks for about, it doesn't say completely equal to, so I'm happy with that. It then asks you to identify the fundamental units of gamma. So we know that 4 gamma was the gradient. Therefore, the units of the gradient must also be the units of gamma. Okay, I know that it was a pressure on my y, and it was per meter on my x. But remember, my gradient is y over x. Okay, so here's my y, here's my x. I have to put all of that to the minus 1 so that it's divided by x. Minus 1 times minus 1 makes 1, so this just becomes a metre. So I get a Pascal metre. But it asks for fundamental units, and Pascal is not a fundamental unit. I know that Pascal is the unit of pressure, which is force over area, which is mass times acceleration over area. Mass is kilograms, acceleration is meters per second squared, over area, so that's over meters squared. Okay, so I can sub this bit in for the pascals here. So I've got the kilogram, I've got the meter from here, I've got the per second squared, I've got per meter squared, but I mustn't forget that I've also got an extra meter, and so therefore I've got 1, 2, minus 2, I've got 0 m's, so I'm left with kilograms per second squared. Okay, it says then in part III, in order to find the uncertainty for gamma, a maximum gradient line would be drawn. Please sketch this. So again, it's just like I just showed you. To get the maximum line, we're going to go through the bottom of the bottom error bar, to the top of the top error bar, that's going to get our steepest worst fit line. We don't want to choose the top of the bottom and the bottom of the top, because that's going to be slightly shallower. So long as with our line of best fit, or line of worst fit rather in this case, it still falls through all error bars, it's a perfectly valid line, but it's our worst fit line. So you just want to draw one that looks a bit like that. Then we've got a percentage uncertainty question. It says that the percentage uncertainty is 15%. So state gamma with its absolute uncertainty. So we were told, even if we couldn't prove this, by the way, I'm just going to make a note for the exam. If you're given something like this and you can't answer this part of the question, it doesn't stop you from taking the value and using it down here. So we've got 0.03 plus or minus 15%. So let's split it into 100 parts. So we've got 1%, multiply it by 15 to get 15, and this must be my absolute uncertainty. Okay, and to 3 significant figures, I'm getting plus or minus 0.005. So I've got my value plus or minus my absolute uncertainty. And then it says finally, the expected value is 0.027. Comment on your result. Now this is a new style of exam question that you don't really get very much at IGCSE level. So when we say comment, actually it requires a bit of maths. It isn't a case of just writing some words. So if this was our value and we now know our absolute uncertainty, we can say what our bottom value and our top value of the range is. Because we know that we're saying the value is 0.03, but it may be plus or minus this amount. So if we minus it, we've got this value, and if we plus, we've got this second value. So we know that our gamma, given the uncertainty that we've got, must lie somewhere between these two numbers. Now clearly 0.027 is in between these two numbers. It's within that range. And so therefore our experiment, we can say it's correct. Okay, and that's the kind of comment they're asking you to make there.